This is the fourth video for Chapter 9, and this is really a continuation of the previous video on the central limit theorem. We just saw that if you have a random sample and the sample size is at least 25, you can use the normal distribution. However, there is a little bit more to it than that. You need a little bit more information, and you need some information that you rarely have if you're going to use the normal distribution. Most of the time, we will not know the population standard deviation, sigma. So an estimate has to be used. Now this isn't noted in our text, and I didn't note it in the last video because I wanted to save it for this video, but you also have to have sigma to use the normal distribution. You need a random sample. You need a sample size of at least 25 or more, but you also have to have sigma, and we're going to discuss why in this video. We've already discussed in the second video for Chapter 9 that you can replace the population standard deviation sigma with the sample standard deviation, which was S, to provide an estimate that's close to work. So instead of sigma over the square root of n, you could use S over the square root of n. Now that's what's going to happen most of the time, because in statistics we're using a sample to make an assertion about the population. So we're using a sample mean to make an assertion about the population mean. Well, if you have the population standard deviation, you probably also already have the population mean, because standard deviation relies upon mean, as we saw back in Chapter 3. So oftentimes you're not going to have sigma, you're going to have S. And when we don't have sigma, we can't use the normal distribution, so some things go out the window. One thing that goes out the window is the z-test statistic. We used to use the z-test statistic back in Chapter 7 and 8, especially in Chapter 8 with our hypothesis test. But the t-test statistic is commonly used with means. And we're going to make that division right here. In this particular class, this STA2023 online class, if you're dealing with a hypothesis test for proportions, you're going to use the z-score, the z-test statistic. If you're dealing with means, you're not going to use the z-test statistic, you're going to use the t-test statistic. This is because of the properties of means and their sampling distributions. The z distribution, the normal distribution, doesn't always describe exactly what's occurring. The t-test statistic can be calculated with this formula. X bar is your sample mean, minus mu, which is your population mean, all over S over the square root of n, this estimated standard error. We're going to use the calculator to find our t-test statistic every time. Just like back in Chapter 8, we used the calculator to find the z-test statistic every time. We are using the t-test statistic because oftentimes the t-distribution is used with means. And in fact, in this class, every time we're dealing with means, we're going to use the t-distribution for our hypothesis test. The t-distribution is like the normal distribution. It's symmetric, so it's not skewed left or skewed right. It's unimodal with one peak in the middle, and it's bell-shaped. The difference is that its tails are thicker. This area that we have on the left and right, it's a little bit more in the t-distribution than the normal distribution. And the t-distribution is not uniform. It can vary. This thickness can vary. The thickness depends on the degrees of freedom, which is equal to n minus 1. And we have several t distributions here drawn under the normal distribution. This shortest curve, this t curve, has a df, a degrees of freedom of 1. That means the sample size is 2. 2 take away 1 would give you a degrees of freedom of 1. So you can see, if I trace over it in blue, this is that t curve, df1. It's shorter than the normal distribution, which is up at the very top, and its tails are thicker. But as you increase the sample size, this degrees of freedom of 2 comes from a sample size of 3. It's a little bit closer to the normal curve, that middle peak, and the tails are a little bit thinner, getting closer to the normal curve tails. And then as you bump the sample size up, this df of 5 comes from a sample size of 6. 6 take away 1 is 5. That would be this peak. It would be these tails. So there's just a little bit less room in the tails with that. So as you increase your sample size, you get closer and closer to the normal curve with your t-curve. And in fact, at a certain point, it becomes difficult to distinguish the normal distribution from the t-distribution. Here I have two distributions on top of each other. There are two here. They're just so close it's tough to see. I've got, first off, n01, that's the standard normal curve, mean of 0, standard deviation of 1. And I also have a t-distribution with degrees of freedom of 40. So n would be 41. And they're almost exactly on top of each other. They're not quite. If we could zoom in, we could see some slight gaps here and there, the peak and in the tails. But from this distance, they look approximately the same. I know this is confusing. Just to narrow it down, the main point to remember, you must use the t-distribution when working problems when the population standard deviation is not known and the sample size is small, less than 30. The general rule that most statistics courses use is that if sigma is not known, then using the t-distribution is correct. If sigma is known, like it was in our previous videos, then using the normal distribution is correct. And this is what I expect you to do. If you know sigma and your sample size is large enough, then use the normal distribution. If sigma is not known, then you're going to use the t-distribution, regardless of the sample size. Right? So let's look at some examples of confidence intervals and hypothesis tests using the t-distribution in the next couple of videos.